thank you all for getting up this morning and coming out to see me talk. I'm going to give you sort of a brief overview of the sun and the solar wind and some of the exciting things that go on in the sun. Since there's only an hour, I won't be able to go into a ton of depth, but I hope that I'll show you sort of the most exciting parts and the best overview so that you can go learn about it more on your own. Okay, so first I'll introduce the sun, then I'll talk about magnetic fields because they're very important. Then I'll actually get to talking about the solar wind. There's a lot of things that I need to do to lead up to that. Then we'll talk about solar activity and a little bit about space weather. So this is the sun, as most people know it. It's just a large glowing ball in the sky. It's actually been around a lot this winter, but it's not really warming us up much. So here's some fun facts about the sun. The sun contains 99.8% of all the mass in the solar system, so it's huge. You could fit 1.3 million Earths inside the sun. It's creating 386 billion megawatts of energy. That's huge. And the core of the sun is more than 150 times denser than water. It's mostly made up of hydrogen, with some helium and a very small fraction of heavier elements like carbon, oxygen, iron. And those are the things that I study in my everyday life, are the less than 1% of what the sun is made of. Okay, so if the sun were just a gaseous ball in the sky, the temperature of the atmosphere would be quite cool. And as you move away from the core, the temperature would just fall off with radius. You wouldn't have sunspots or a solar cycle. And also radiation from outside the solar system would be able to easily penetrate in. But the good news is that the sun is not just a gaseous ball. There's more than meets the eye. And now I'm going to switch over to a little movie here. So recently in 2010, the Solar Dynamics Observatory launched. And it has been providing us unprecedented views of the sun. And so while this view is less kind of interesting than some of the ones that you're going to see, this is the photosphere. And what you see on the yellow photosphere, which is what we see in visible light, are some dark spots, and those are sunspots, and I'll describe them in more detail in a little bit. But as you look with different filters, which look at different wavelengths at different areas of the sun, you see all sorts of different exciting things showing up. For example, if you look at some of the iron lines, what you start to see is some structure on the surface. And it turns out that that structure is related to the magnetic field. And so you have fields that are coming out of the surface, fields going into the surface, and so it's quite a mishmash of magnetic fields. If you look at other filters, you start to see an atmosphere appearing above the limb. And you start to see all sorts of different structures where there are sunspots. There are these loops that are hot and glowing up higher in the atmosphere, and they create big, bright atmospheric enhancements. And so we're going to talk about some of those things today. But this is one of the fun SDO movies that recently came out showing how the sun looks in all sorts of different wavelengths. So it's not just this yellow gaseous ball. It's actually very dynamic and very active. So we'll go on to talk about all these different aspects of the sun, the sunspots, the hot regions, the cool regions, the exploding regions. But before we do that, we need to talk about magnetic fields, because magnetic fields are really the key to all this sort of interesting stuff that's going on in the sun. So there's essentially two types of magnets, or two main types of magnets. You have permanent magnets, which are, like iron, ferrite, magnetized permanently. And then there's electromagnets, which are basically formed by currents flowing in material. So you guys have probably sometime in your life done this experiment, and if you're young, you might do this experiment as you get a little older in school, where you put down a bar magnet, and then you kind of just toss some iron filings on a piece of paper. And what you find is that the iron filings will align themselves with the magnetic field, tracing out these paths. And so those magnetic fields there are really important to the dynamics of the sun. So kind of more schematically, you have the magnetic field with field lines flowing from the North Pole to the South Pole, creating these loops that start at one end and end at the other. They're always continuous loops. You don't have any magnetic monopoles going out with magnetic fields not connecting somewhere else. So as we go forward and I talk about open magnetic fields and closed magnetic fields, keep in mind that they're all closed. Just some we call open, they just connect way out, far away from the sun. I'm not inventing magnetic monopoles. Okay, so electromagnets, these work when you apply a current in a coil, such as or a conductor, which is, in this case, a wire. As you run a current through this wire, it's going to generate a magnetic field. It looks a lot like the bar magnet. It behaves a lot like the bar magnet, but it is generated just by moving charges. And so this is the sort of magnet that you would have in an MRI or other things like that. And so just as an example, I have this fun magnetic field mapping demo. I'll try not to electrocute myself with it. All right, so what we have here is a coil of wire, just like that schematic just showed. And I'm going to run a current through it, and all of these are magnetized little rods, and they're going to align with the magnetic field. Right now, they're just sort of aligned with, well, they're just sort of random. If they were really on sort of like frictionless mounts, they would align with the Earth's magnetic field. But this is going to be fun, so hopefully I won't get shocked. A little shock. All right, so here we are. So you can see that sort of dipole pattern where you have the field coming out of the center and then arcing around. Actually, I think if I take it off, it still stays there with a little bit of sparking. So anyway, you see how when you run a current through a conductor, you get a magnetic field. And so these currents are going on in the sun, and they are how the sun's magnetic field is generated. And so just for kicks, I'll erase these field lines, just because this is fun. And we'll do it one more time. So no current, and here's a current. All right, so anyway, so that's how the electromagnet works. All right. So if we think of the sun then as this electromagnet, at solar minimum, which I'll talk about in a little bit, that's when the sun is at its kind of least active phase. The sun's magnetic field does look a lot like this dipole, where you have the North Pole at the south and magnetic field lines, well, it's either at the north or the south, it flips over time, but magnetic field lines running from north to south. And so that is what the simplified structure of the magnetic field looks like, the global structure. So how is that magnetic field generated? Well, let's first talk about the structure of the sun, then we'll talk about how that's generated. First, at the center of the sun is the core. Basically, the core is very, very high density, and it's where protons are fusing, creating helium and releasing energy. And basically, that's the energy source for the sun, and it is like 15 million degrees Kelvin in there. It's very, very hot. And it's going to be able to burn hydrogen for like another 5 billion years. As you move out from the core, you get into the radiative zone. And that kind of starts here, and it goes to approximately this area here, up at the top where it changes to orange. And in this area, which is called the radiative zone, you have plasma. Since it's hot, it's charged gas, so that's plasma. So you have plasma that's absorbing and re-emitting energy from the core. So basically what happens is that as the energy is moving out, it's just absorbed and re-emitted as it moves away from the center. And that process actually takes, so for energy that's generated in the core, it takes 200,000 years almost for the energy to make it to the edge of the radiative zone. So if fusion stopped in the core, it would take a long time for us to realize that. Although there's other things that would go on. But just in terms of, there's a few other things that would happen. But in terms of energy transfer from the radiative zone. Okay, so anyway, so as you move out, so you get to the edge of the radiative zone. Well, the core and the radiative zone are spinning because the sun spins. And they're sort of spinning rigidly, as you imagine, like a golf ball would as you hit it through the air, with a lot of backspin on it. Anyway, so the inside is rotating rigidly, and that's due to the angular momentum of the solar system from the formation and everything. But then you get up to the upper part where you see those loops, which are signifying convection. And this part here is not rotating rigidly. So what happens in this region here is that you have this plasma here. It's being heated from below. And this is essentially like the radiative zone is like the burner on your stove. And the convective zone is like the pot of water. And so you heat it from the bottom, the water starts to boil, or the plasma starts to heat, and you start to set up convective patterns where plasma gets heated, it rises up, it cools, and then it falls down, and so you set up these convective patterns. So you've got this convection going on that's pulling plasma up, and then it subducts down. And we see that on the surface. We can see plasma welling up and plasma going down. But anyway, so this part of the sun, the convective zone, rotates differentially. So what that means is that the parts near the equator are going to rotate faster than the parts near the pole. So you've got this differentially rotating outer layer, the convective zone, and this rigidly rotating internal region of the radiative zone in the core. And what happens then, because this is all hot and charged, is that you basically set up currents. So you have moving electrons and protons, and they drive currents. Those currents manifest themselves as magnetic fields. So on Earth, the magnetic field is coming out of the iron core. And it takes, I think, something like 100,000 years for the poles of the Earth to flip. So over time, if you've ever heard of this, the North Pole actually is moving, maybe a few inches per year or something. And I think it basically, the fact that it takes 100,000 years has to do with the fact that it's rooted deep in the core, and it takes a long time for that, the pole or that core to kind of rotate in a way that flips the poles of the Earth. On the sun, it only takes 22 years for the magnetic field to flip its orientation all the way around. And so because that change is so short, we knew that the location that the magnetic field was generated in was much closer to the surface. And so people postulated that there is this region where you basically go from differential rotation to rigid rotation, and that's where you generate the magnetic field. That region, in case you're interested, is called the tachocline. And so that basically is where you have this differential flow. Okay, so how does that differential flow create interesting things on the sun? Well, this is sort of a simplified model of the magnetic field in the sun. So if you imagine that it starts out as a magnetic dipole, and then you have differential rotation, it's going to start to pull some of the fields a little bit faster. And essentially it wraps them up around the sun. And when they become wrapped enough, sometimes there can be instabilities, and then the fields will basically kink out. And when they kink out, that is supposed to be basically the formation of a sunspot. And so you get these loops that rise up above the surface, and then the theory, the Babcock theory, basically says that these loops get bigger, they move up towards the pole, and they're responsible for transferring the magnetic field from, say, being northward directed to being southward directed. And they do that through the formation and movement of sunspots. So if you imagine then that you have these little bipoles on the sun, which is equivalent to maybe something that would be generated from a horseshoe magnet, those are the areas that you have sunspots. And so For example, these dark regions here, right there, that little dark spot, that is a sunspot where you have very strong magnetic fields. And then there's some other features here, filaments. Those are kind of cool plasma that's supported on these ropes of magnetic flux. And active regions are bright regions around sunspots that are typically hotter. All right, so let's talk about sunspots. So the sunspots basically exist because of the sun's magnetic field, and they are cooler, dark regions on the sun. The reason that they're cooler is that basically the magnetic field inhibits some of that hot plasma from rising up. And so where the fields are the strongest, that's where you have the most inhibition or inhibiting of the warm plasma rising up. So you get the dark spots that form. They have very strong magnetic fields. And these are the regions where you can have a lot of unstable magnetic fields, and they can actually explode and expel plasma and magnetic field into space. So this is just a little drawing of how these magnetic fields emerge from below the surface, and they expand out and connect to other sunspots. So basically you need a sunspot pair or a collection of sunspots because the field comes out and will connect to those other sunspots. And so this is a trace image of these loops on the sun. So this is looking at the edge of the sun, which is marked there. It's the limb, and these bright loops are filled with plasma that's streaming back and forth across them. Sometimes there's collisions of the plasma down low that leads to these brighter emissions, but the sun, you can see, has a lot more going on than it appears in the sky. So now let's talk about the solar atmosphere. So people first found out that the sun had an atmosphere because they started looking at eclipses. And this is a painting by Antoine Caron in 1571. And this is a painting of some astronomers studying an eclipse. And you can see the kind of the bright region around the sun. And that is the sun's atmosphere. Now we have we can actually make eclipses, or we can, photograph them and see much more detail. But that bright area there that's around the sun and these streaks that are coming out of the sun, that's all related to the atmosphere. So we looked at the interior of the sun. We had the core, the radiative zone, and the convective zone. So that's the interior of the sun. And then we can move out and we'll talk about the atmosphere. So we looked a little bit at the photosphere, and that's where you see the sunspots, and that's the part that's visible to the naked eye. Then as you move up, you get into the chromosphere, and some of the things that appear dark there are that cold plasma sitting on magnetic flux ropes. And then as you go higher up, you get into the corona, and this is where you see, all sorts of protrusions off the limb of magnetic fields and bright spots over some of those magnetic fields, and then you see some dark spots over the poles where there aren't these big loops, and those are coronal holes. So the center of the sun is 15 million degrees Kelvin. As you move out, you get to the photosphere, it's about 6,000 degrees. So this is a plot of the temperature. I have to show you some plots because that's what I look at most of the time. This starts below the surface. I don't think it makes it all the way, it doesn't make it all the way into the core, but basically as you come out to the surface, you get down to 6,000 degrees here in the photosphere. That's the coolest region of the sun, temperature-wise, not the coolest region, phenomenon-wise. Anyway, as you move up in the atmosphere, something very strange happens. If you imagine that you're moving away from a source of energy, like the further you move away from a campfire, the colder you're going to get. Well, imagine that you move away from the campfire and all of a sudden you're in another hot region and there's no fire around. It's very confusing. So that's basically what happens when you move into the corona. All of a sudden it gets super hot, up to about 1 million degrees Kelvin. And so this is really confusing because there's no fusion going on here. But this is basically the key to the solar atmosphere. So when people looked at eclipses long ago, or really say any time before the 1900s, and they saw this big kind of gaseous glow coming from around the sun, they did actually postulate that the atmosphere might be really hot, because in order for it to expand so far out into space and for you to be able to see it, it needed to be really hot. And so, so this million-degree corona is where some really interesting things happen. So what happens is that you have a lot of energy that's created in the corona, and the ways that the energy is created are still debated today. But two of the main theories are basically the dissipation of energy from magnetic fields reconfiguring. That's called magnetic reconnection. But basically, it's magnetic fields kind of catastrophically rearranging and changing connections, releasing energy. And the other method for heating is the damping of waves. So as waves propagate and they damp, they turn their sort of kinetic energy into thermal energy and can heat plasma. So that energy then is moving out of the corona. So here's another fun eclipse image. Shows these rays coming out of the sun. So it's been long known from the eclipse observations that we have an atmosphere for the sun. And then eventually spectroscopic measurements confirmed that the temperature of the corona was 1 million degrees. And so what you have is this hot, high-pressure corona sitting in the middle of the near vacuum of space. So space is very cold, space is very low density. It's not a complete vacuum. But what happens then is that you have a flow that develops that blows from high pressure to low pressure. And that flow is the solar wind. And so it's born in the upper atmosphere of the sun and basically carries out material in that region. And if you study it, you can actually understand the processes that are going on in that region, try to understand how it's accelerated. So the solar wind was really first postulated by Richard Carrington and George Fitzgerald and a few other folks after they witnessed the geomagnetic storm in 1859. So this was a huge event called the Carrington event. And what happened was there were some big solar flares that went off in the sun, and so people studying the sun saw these huge flares. 3 to 4 days later, all of a sudden, there were all of these weird things going on Earth. You had huge auroras that were sighted, or northern lights, that basically were sighted at really low latitudes. Usually they're confined to the polar regions of the Earth. And so they were sighted, very low, like, I don't know, down to Kansas or something like that. I mean, it was a huge event. There were some fires going on that happened in a telegraph station. Basically, currents started flowing in the telegraph line that overloaded one of the stations and caused a fire. There were just a lot of weird things that happened. And they started to say, well, this is weird. Seems, coincident that there was this solar flare, and then we're having all these weird kind of effects on Earth. So, well, maybe the sun's influence reaches out into space through something like a solar wind. So later on, the solar wind was actually observed by Ludwig Biermann, and he explained the existence of a comet's two tails as being driven by both the motion of the comet and by the solar wind. And so in this picture, what you see is a comet moving in this direction down here. It's got a dust trail or tail that's kind of streaming out behind it opposite the direction of flow. And then there's this other very straight looking gas tail. And that tends to point opposite the direction of the sun. And so what happens is that the dust tail is made out of neutrals, and it just doesn't care about the solar wind really. But the gas tail is charged, and the solar wind takes the magnetic field of the sun and drags it out into interplanetary space. And so what happens is that anything that's ionized sees the solar wind and basically can be picked up and dragged with it. And so this was one of the first ways to confirm the existence of the solar wind. Parker later was he basically coined the term the solar wind, and he derived that the solar wind has to be supersonic in order to overcome the sun's gravity. Basically, he set up sort of an equation of motion that balanced pressure and gravity, and what he found was that in order for the sun to make it out of the gravitational potential of the sun, it needed to become supersonic. And so we have confirmed today that it is supersonic, and we regularly observe the solar wind. So I wanted to show a quick movie from it's one of the Stereo spacecraft. So Stereo launched in something like 2007 or 2006. And basically it's two spacecraft that launched from the Earth. And they started moving out. I'm going to go to the board here. If this is the sun here, and this is the Earth, basically Stereo launched, and one started moving in that direction, and one started moving in this direction. And they basically are orbiting the same distance away from the sun as the Earth, but they basically were providing stereoscopic views of the sun. And one of the experiments on the Stereo spacecraft is a heliospheric imager. So what that means is it's not looking at the sun, but it's looking kind of away from the sun, looking at the flow coming out. And they've caught some really interesting images and movies. And so the one I'm going to show you is an image of, here it is, a comet. So this was recent. I think it's the end of last year. It's Comet Ison. And so for reference, so this is, I think it's Stereo A. You can actually see the Earth in the field of view because it's looking kind of perpendicular to the sun. So the sun is somewhere off here to the right. There's the Earth, and here's the comet coming in. And if you watch the comet tail, you could imagine that if the comet was moving through just a vacuum, its tail would just be steady behind it. But you'll notice that there's actually a lot of motion. The comet's moving steady, but the tail is sort of whipping all over the place. And there's actually another comet that shows up in front of its comet Iki. But you see the comet tail kind of flapping in the breeze and sometimes even breaking off. And that's basically due to the solar wind blowing past it. So we're still using comets to study the solar wind. So here's some facts about the solar wind. So it's continuously emitting about 1 billion kilograms per second, or 1 million tons per second, into interplanetary space. It has speeds of around, on average, 400 kilometers per second. That's maybe equivalent to about 1 million miles per hour. That's, if you were traveling with the solar wind and you were using it to move around Earth, it would get you from Detroit to Mackinac in a second, so that's very fast. It consists of charged particles because they're coming out of that 1,000,000-degree corona where pretty much everything is ionized. It's quasi-neutral. In other words, there's about as much positive charge as there is negative charge, so it's got protons and electrons as constituents. Something else that's sort of interesting is as the solar wind blows away from the sun, it carries the magnetic field of the sun out into space. Now, the sun is rotating, and so as the sun rotates, the magnetic field is rooted in the sun. It actually creates a spiral pattern for the magnetic field. So the solar wind is moving radially outward and carrying the magnetic field, but the magnetic field is creating a spiral, and that is called the Parker spiral. And we can observe that with spacecraft. And so the magnetic field and the solar wind are flowing out into interplanetary space. And basically what it does is it carves out a region of space around the solar system that's called the heliosphere. Helios from sun. Sphere is pretty self-explanatory. And so inside the heliosphere, the sun is dominating all the processes that are going on. Beyond the heliosphere is interstellar space. And I'll talk a little bit about the heliosphere in a couple slides. All right, so we showed that dipole magnetic field of the sun before. Well, It doesn't really look like that. Because there's this solar wind that drags the magnetic field out, you have kind of this distended dipole where the magnetic field comes out over the poles and extends off to the edge of the heliosphere, and then the fields that were closed down here, some of them are still closed close in, but others are pulled out and they extend out into the heliosphere. So we can launch a spacecraft and measure the magnetic field in the heliosphere and measure the solar wind right nearby the Earth, as soon as you get outside the Earth's magnetosphere, or the influence of the Earth's magnetic field. Oh, this is, so something that happens when you have magnetic fields kind of being pulled out is that you get, basically you come to a point where you switch polarities, where the magnetic field switches from being flowing away from the sun to flowing into the sun, or the direction. And when that happens, that's called the current sheet. And so we can observe the current sheet. And there's some special things that happen at the current sheet, but this is one of the ways that we confirm that this is what the configuration actually looks like. So there's been a number of spacecraft that have been launched to study the solar wind and the sun. So as I said, the solar wind is carrying along the frozen-in magnetic field into the heliosphere. What we found with the Ulysses spacecraft, which was launched in 1990, and it basically, when it was launched, it flew out to Jupiter, and then it used Jupiter to gravity assist itself into a polar orbit over the sun. And so it went between the orbit of Jupiter and then just outside the orbit of Earth, and went up to 80 degrees plus or minus latitude around the sun. So that gave us the first 3D view of the heliosphere. And actually, really, it's one of the only 3D views of the heliosphere that we've had, because everything else tends to orbit in the ecliptic plane of all the planets. So anyway, so what it found during its first pass over the poles of the sun and around through the equator is that there's basically two types of solar wind that it encountered. One was a fast wind. So this is a plot. It's a little bit confusing. Here's the sun at the center. These concentric rings mark speeds. So basically, the further out you are away from the center of the sun, the faster you are. And so this is just superimposed with a picture of the sun. But anyway, so as it was going over the poles, it saw fast wind. And then as soon as it got down towards that current sheet, you started to see much slower, more variable wind. And then you get over the poles and it goes back up. So this is a solar minimum. When the magnetic field is simpler and it's more dipolar, you see that there's fast wind coming from over the poles and slow wind coming from the equatorial regions. And so these are the two main types of solar wind that we're still trying to figure out how they formed. And the characteristics of this solar wind vary with the solar cycle. I'll talk more about the solar cycle, but just kind of in a very basic sense, at solar minimum, the magnetic field is well ordered like a dipole. In theory, it's very dipolar. At solar maximum, it gets much more complex and is just not really well ordered at all. And so when Ulysses did the next polar pass over the sun, it did it during solar maximum, and there was no longer this well-ordered solar wind. You had a lot of fast and slow streams right next to each other, and that's characteristic of solar maximum. A lot of kind of disordered behavior on the sun. So we broke the bubble that the sun does not actually have this perfect little dipolar magnetic field. Well, it turns out the Earth doesn't really either. Because of the solar wind blowing past the Earth, it actually takes the magnetic field of the Earth and it stretches it out into sort of a windsock shape. And so here's the Earth at the middle. This is the part of the dipole that's in the front, still looks like a dipole, like loop field, and the rest of it kind of is stretched out into this elongated shape, and it sort of closes on itself very far down in what's called the tail. And I have some movies later on that maybe we'll get to that show that this is actually a very dynamic shape. Because the solar wind varies so much, it actually will compress and basically it compresses the magnetosphere, and then the magnetosphere will expand and compress, and it really does wave in the wind. I won't talk about much more detail about that. Well, it turns out that there's also sort of an interstellar wind. Really what it is the motion of the sun through the local interstellar medium. And what happens is that you have a heliosphere that forms, we talked about that, but that also gets elongated into this bubble-like windsock thing. And that's just due to the motion of the sun through space, the nearby interstellar space. And we have two spacecraft that may or may not have passed through this edge of the heliosphere. People are, very much still debating whether or not they've passed through. But Voyager 1 and Voyager 2, which were launched in the 70s, are basically out at that boundary, very near it or past it. So, and it's amazing. They're still working. They're still sending back data. The scientists that are working on it are still working on it. They started off as young lads and lassies and are now approaching retirement, but they are waiting till it passes the heliopause, the edge. All right, so why are we interested in studying the solar wind? Well, it turns out that you can actually learn a lot about the sun and its atmosphere by studying the solar wind. So you can look at images. I mean, I've shown you a lot of images. I personally do not work with the spacecraft or the instruments that provide the images, but they're just so much better public relations tools than the squiggly line plots that I work on. But what I do work on is in situ measurements. And so what that means is we launch a spacecraft. Often it'll either be like Ulysses, where it does this polar orbit, or Stereo, where it orbits around kind of in the orbit of Earth. There's also a point that we put a lot of spacecraft that's called the first Lagrangian point, and it's basically at the gravitational saddle point, or like where the gravity between the Earth and the sun balance. And so that's a lot closer to Earth because Earth is really small. It's actually 1/215th the distance to the sun. So anyway, so we put spacecraft there, and we have sensors on them that collect the solar wind and then measure what it's made out of. And so that's the stuff that I do. And so these in situ measurements, where there are spacecraft that are sitting there collecting the solar wind, they can be used to infer the temperature and the densities and the velocities in the corona, which can tell us about the processes that are going on there. Specifically, I look at heavy ion measurements, and they're a very useful tool to study the origin of the solar wind and how solar eruptions happen. Some key open research questions that the community is working on are what heats and accelerates the solar wind? This has been an open question for many, many years. What causes large solar storms or coronal mass ejections? And what accelerates energetic particles, which are also called high energy radiation? So those are the things that we write proposals and center our work upon. All right, so I'm going to move on and talk about some sunspots now in the solar cycle, because some of the really exciting stuff happens when you start talking about solar activity. So the sunspot cycle is basically 11 years, and it's related to the flipping of the pole, the magnetic field of the sun. And so it takes approximately 22 years for the sun's magnetic field to go from north to south to north to back to north to south. And in that 22 years, there's two spikes in the sunspot cycle. And when it's mostly dipolar, like the simplest configuration, there's very few sunspots. And as that field wraps up and the sunspots pop out, the magnetic field becomes much more complex. And that's solar maximum, when there's a ton of sunspots. And so all sorts of exciting things like that big solar storm that led to the postulation that there is a solar wind, that Carrington event, happened at solar maximum. And so this is showing, it doesn't go back super far, but it goes back to 1790, and then it shows our current solar cycle, which is actually a lot weaker than the one that happened back in 2000, 2001. We had a huge storm in 2003 that was called the Halloween event. As it happened right around there. There was a Bastille Day event. I mean, we like to name these off of, worldwide holidays. But if you go back even further, you can see that kind of the amplitude or the height of these curves varies. And so if it's really tall, then it's really active, and if it's kind of short, then it's not that active. There actually was a period back in the 1600s when there were very few sunspots for a long time. I think it was something like 100, 200 years. And that was really unusual. And there were some weird things that happened on Earth that may or may not have been related. It's sort of a bag of worms when you open it up, or a can of worms, because there was like this little ice age in Europe where things got super cold, and people thought that maybe it was actually related to this really low activity on the sun. And so, but that sort of brings out questions of global warming, and that's a mess. I don't want to go into it. But I will say that this most recent winter is not the sun's fault. But anyway, there may be some small tie in between the sun, solar activity, solar brightness, which varies with the activity level, and and some changes in the Earth's climate, but it is definitely not the main driver. So what does the sun look like over the solar cycle? Well, it goes from being fairly featureless at solar minimum to having lots and lots of bright areas and kind of hot, big loops in solar maximum, and then it decays away back to that sort of quiet state. Something that's kind of interesting here is this last solar minimum, two solar minimums ago, was very quiet. Looks like, there's very little stuff going on in the sun. But as you come around and you start to go into the next solar minimum, there's actually a lot of bright stuff hanging around. This was a very unusual solar minimum that just happened. It ended in around, or I think it bottomed out in about 2009. Things were particularly weird. The magnetic field wasn't really quite as dipolar as we had hoped. The magnetic field strength was really low, though, and the solar wind was super slow. It's something that we're still studying. All right. So moving on. So this is the current solar cycle blown up. People predicted. The predictions were kind of all over the board. It was either going to be very big or it was going to be very average, but it turns out that it's actually under all the predictions. It's very non-remarkable. We've had a few coronal mass ejections, but not really as many as we had hoped, and we had launched spacecraft like Stereo and SDO in the hopes of catching all these big solar storms, but we've only been able to catch a few smaller ones. But the good news is that there's a lot less radiation that's coming off because the big solar storms have a lot of radiation that they expel, and that can damage electronics on spacecraft, so these spacecraft are actually getting much less radiation than they had been designed for. So hopefully they'll last a long time and see the next solar maximum. Okay, so solar activity, just to review, at high amounts of solar activity, you have sunspots, active regions, and these prominences, which is just a magnetic structure that has cool material on it sitting above the limb that can become unstable and erupt. You have solar flares, which are big, kind of catastrophic eruptions of magnetic field, and coronal mass ejections, which are kind of like solar flares, but they're much larger and they release large amounts of material into the solar system. All this stuff is driven by magnetic fields, and the frequency of all these events vary with the solar cycle and vary with time. So the sun is most active during solar maximum. And all these events can affect the space environment around Earth and all the other planets. And that's something that we want to worry about if we're going to send astronauts to Mars, or just even having astronauts in Earth orbit. We worry about sort of the hazards from space weather. So to get into sort of what causes some of these solar explosions, I talked a lot about the magnetic fields and the magnetic kind of reconfiguration. Well, this is just a little graphic showing how the magnetic field can change its configuration. If you have oppositely directed magnetic fields, they attract each other. And when they attract each other, they move together. And what happens is that they can actually, if they get close enough, they can change their conductivity. So a field that was originally just going from the top to the bottom here now actually starts to take on a configuration where it actually loops through here. It's changed its connectedness. It's no longer connected to the original line. It's basically switched its connection. Well, that process releases a vast amount of energy, magnetic reconnection it's called, and that is basically what releases all the energy in solar flares and coronal mass ejections. There's other things going on too, but that's really the big driver. So this is a movie which sort of shows, basically here, this is from Trace. Trace is like an older version of SDO, so the images aren't quite as crisp, but it's still provided a lot of exciting science. So what you've got here is some dark material, which is cooler, and some bright material, which is hotter. And you'll see as I play this that, see those big eruptions and the plasma flowing out. That is basically happening because of this reconnection. And that heating that happens not only goes into the kinetic energy or the motion of the plasma, but it also heats the plasma that's left behind, and so you see it glow. And so this stuff is going on all over the sun in small scales and large scales. And when it's happening on the large scales, you get big catastrophic events. I'll quickly talk about my squiggly line plot, which is what I look at. It's not quite as exciting, but it's got a lot of information. So we have these spacecraft sensors that sit out in space, and they measure the density, velocity, the temperature. Actually, that's the temperature. This is the velocity, the magnetic field strength. Basically, as these lines go up higher, that's larger values. As they go down, smaller values. And then we measure the charge states, which is really where I spend most of my time. But basically, you see the density of the solar wind increases and decreases. These red lines mark boundaries of the start time and the stop time of a big solar storm passing. We see kind of temperatures dropping as the plasma blob expands. As it expands, it cools, and so we see that in the temperature. So you see this big dip here in the temperature. The speeds, basically, as it's expanding, the back of it is moving slower than the front, so you can sometimes see that in the velocity. So the velocity is decreasing as you move back. There's really strong magnetic fields, because we said that these things happen on the sun where there's a lot of magnetic fields that are strong. And then, just to talk about the charge states, without getting into too much detail, we said the corona is 1,000,000 degrees. Well, it turns out that if you have like an oxygen ion or an oxygen atom sitting in a 1,000,000-degree corona, it's going to have 6 of its electrons ripped off. If you remember, oxygen has 8 electrons total. Well, in a 1,000,000-degree corona, due to collisions, you're going to lose 6 of them. So if it gets even hotter than that during some of these solar storms and these big reconnection events, you could actually fully strip off all the electrons off an oxygen atom, and then you have like oxygen 8+. It's called. Iron often exists with 16 electrons ripped off of it. If it gets hotter, even more get ripped off. So basically, what you see here in these plots, and I don't expect you to, walk away being able to explain this, but is that in the solar wind, the charge state kind of sits around steady, and all of a sudden you enter into this event, this storm, and you see all the charge states shift up, and that just tells you that there was a lot of heating in the corona where these things happened. Once the plasma expands beyond maybe 4 solar radii, then there's not enough plasma around for there to be collisions, and so these things, the charge, basically it doesn't ionize any further. And so we can use the charge states to kind of get into what the conditions are back at the sun. All right, enough of the squiggly line plots. All right, so I've got about 10 minutes. There's a couple cool movies I want to show you. I'll show you just a little bit of this 3 years of SDO. So SDO now has been I think it's celebrated its 4th anniversary on February 11th, but this is 3 years of SDO. NASA heliophysics, they're our governing body for NASA. So as the sun turns and as the time changes, you'll see the bright spots moving around, there's more of them at times, less of them. But you can see, the sun is just way more complex than that yellow ball. one of the more exciting things that's happened recently is that we've caught some really interesting things on the sun. If I can get to the next slide. Okay, there we go. So over the last couple of years, we've seen a couple solar tornadoes, and these have been pretty cool. And this all still kind of has to do with the magnetic fields of the sun. This is 2012. So you see this plasma rising up above the limb of the sun, and it's twirling. And this is like the size of the fiber of the sun. So this stuff is pretty exciting. All right. All right, so one of my colleagues reminded me when I saw the title of my talk that sometimes the solar wind actually sucks. And so as the solar wind is blowing by all the planets, it's interacting. I showed you how it kind of interacts with the magnetosphere by stretching it out, and there's actually a lot of effects that happen. But for planets that don't have magnetic fields to protect them from the solar wind, what happens is that the solar wind can actually pull parts of the atmosphere off. So this sort of the bright area around Mars, this is around Mars, is the atmosphere of Mars. And you can see that the atmosphere is actually being stripped off by the flow of the solar wind. It sort of looks like, I mean, if you think of sort of fluid mechanics, it's like, it's just like a sphere in a flow. I mean, you're ripping off, you've got separation of the flow and mixing of the flow behind it. All right, and then I've got a couple more minutes here. I hinted at space weather, but I haven't really talked about it in great detail. So I'm going to spend the last couple minutes showing you a movie that I actually had made for an exhibit at the Detroit Science Center. It doesn't have a narration, but it has subtitles, and I'll kind of talk you through it. But let's get it to full size. And this sort of is going to go over kind of how, like what space weather is. And it all starts with the sun. Oops, this is not it. Wait. Escape. Oops, not that one. There we go. Hopefully that thing will go away. Okay, so the sun, large magnetic ball of gas. It's got a magnetic field. I wish this thing wasn't in the way. That magnetic field is pulled out into space. This is just essentially a summary of what I've told you. These magnetic fields can become unstable and erupt. And sometimes if they explode out of the atmosphere, then they become coronal mass ejections. This is another SDO movie, which shows this huge kind of filament basically activating, and all the magnetic fields kind of lighting up around it. It was that big structure that happened across the sun. This is an image of one of these big loops that can be seen on the sun. So here's an animation of how, if this big loop becomes unstable, it'll blow out, become a coronal mass ejection. As it expands, it accelerates particles. That's high energy radiation. It can flow out and hit different planets, spacecraft. Then the magnetic field and the plasma contained within the coronal mass ejection can float by. Our spacecraft measure it. They measure the different parts. Then it hits the Earth. So one of the things that's interesting is as the solar wind and the coronal mass ejections hit the magnetic field of the Earth, it will compress it. And you have geostationary basically satellites in geostationary orbit, and they are protected by the magnetic field of the Earth. But when you have big pressure pulses that come with these storms, you can actually push the magnetosphere inside the orbit of some of these spacecraft. And so if they use the Earth's magnetic field for any sort of navigation, all of a sudden they get totally confused and they have no idea where they are. Not to mention they're exposed to a lot of radiation. And so those solar storms, they create aurora, and this is an image of kind of how the aurora is evolving as a storm is hitting the Earth. It creates the northern lights and the southern lights, which is very beautiful. But it does cause a lot of danger for astronauts and for spacecraft. And even if you're flying in an airplane, you can get more radiation. Power grids can experience problems as the magnetosphere basically reacts to the solar wind. As you compress a magnetic field, currents are driven in the ground or along any long conducting wire to basically try to counteract that change. And so when that happens, you can have power grids that fail. And so that little image of the Earth going black was a very extreme. That's basically, if the Carrington event happened today, you could have a massive power outage like that. All right. I'm actually going to skip this. I will show you this Solar Orbiter movie if you want to stay for a couple minutes. I'm part of this mission, Solar Orbiter. It's going to be launched in 2017. It's a joint European Space Agency and NASA mission. And so I'm part of a team that's building a sensor for that. But I'll do that after I end, just in case people need to get out of here on time. But this, if you didn't get the summary from the little movie I just showed, I think you can kind of figure it out from here. The sun, it's not just a smiling happy face in the sky. It does provide us energy and it gives us sunburns. The sun thinks it's pretty awesome. It's throwing off these huge solar storms, but really we're just a little spot on the edge of the galaxy. So keep it in perspective.